All right, so welcome to part 3 of lecture 7. And now we're going to see how we can use this polynomial identity testing algorithm or this lemma that we saw to give a randomized algorithm for matching problem, right? So, okay, so here's the problem. Suppose that we have a bipartite graph, okay, G, and the bipartition of the vertices is like the left edges and the right edges. Sorry, the left vertices and the right vertices, right, with edge set E, where the size of L is equal to the size of R, which is equal to N. And the question that we're interested in is whether G, the graph G, has a perfect matching, right? So for example, we can give like 2 examples of graphs, right? Like we can have this graph here, right? So this is, let's say, graph G, and we can have graph H, which, as you're going to see, I'm just going to construct it in a way that you can already see that, okay, so what is the difference here? Well, G does not have a perfect matching, right? Like no perfect matching. And H has a perfect matching, right? I could have matched like this, right? And a matching is again is a disjoint set of edges, right? The edges must be disjoint, and a perfect matching is one that covers all the vertices. Okay, so this is a problem that's familiar to all of us, right? And here's the question, right? So now, if you remember from any graph, right, and in particular bipartite graph, what can we do, right? So if I have these graphs, what I can do is to each of these graphs, I can associate its adjacency matrix, right? So in this case, what is the adjacency matrix here of G? Let's say the matrix here will be, I will put the left vertices, the left set of vertices here and the right set of vertices here, right? So we have, let's say, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then we can construct the adjacency matrix, which I just put 0 if it has no edge, and 1 if it has an edge, right? So 1 has an edge, 1 from the left has an edge for everybody, and 1 on the right has an edge for everybody. Everything else is 0. And similar for H, right? But the difference from H here is what? Well, if I create the adjacency matrix, what we have is we have our matching, which is 1, 1, 1, and then we have the other edges, right? So for example, 1 is also paired up with 2. There's no edge between 1 and 3. 2 is only connected to 2. And then 3 is connected to all of them, right? So you can see that this is a perfect matching. Yeah. So the red edges, the edges that we like saw, they form the perfect matching, right? So how do we decide if a graph has a perfect matching, right? You probably learned like many algorithms for this, and I'm going to teach you one more, right? So here's what we can do. So instead of looking at the adjacency, only the adjacency matrix of the graph G, here's what we can do. We're going to look at the symbolic adjacency matrix. Okay, so this is going to be like the symbolic, what we're going to call the symbolic adjacency matrix of G, right? Of the bipartite adjacency matrix. And what is that? This matrix now will be, this X will be an n by n matrix such that Xij, the entry, the ij entry of this matrix X is going to be a new variable, a variable Yj, y of ij, if there is an edge between I and j, or 0 otherwise, right? So here's, again, if we look at our graph G, we had this, and then this here, right? So this is our graph G. Now, what is the matrix that corresponds to it? So X of G will be the following matrix. We will have Y11, Y12, Y13, because 1 is connected to 1, 1 is connected to 2, 1 is connected to 3. Then we have 0, right? Sorry, not 0, like 2 is connected to 1, so we have Y21 and 0, 0. And then 3 is only connected to 1, so we have Y31, 0, 0. So each of these variables Yij, they're distinct, right? So we're creating the symbolic adjacency matrix of the graph. Does that make sense? Okay, so now here's the thing, right? Now, if we compute the determinant of this matrix, what do we get, right? So if you remember the formula of the determinant, right? The formula of the determinant is what? Is the sum over every permutation of the sign of the permutation. So this is just my notation for the sign of the permutation. Times the product of the entries xi sigma I, right? So this is the formula of the determinant that you all know. But if you notice, right, like what is this monomial? What is this monomial of the determinant? Like this monomial corresponds to a matching. Corresponds to a matching, to a perfect matching. In the graph, in the complete graph, right? Because if you notice, what is a matching? A matching is nothing more than a permutation, right? A matching in the graph. So let me just show the correspondence here. Like, okay, let's say that we pick a permutation, right? Let's pick a permutation 1, 2, 3, right? Like 1, 2, 3 is our permutation. The permutation that maps 1 to 2, 2 to 3, and 3 to 1. What is the matching corresponding to this permutation? Well, I link 1 to 2, and then I link 2 to 3, and I link 3 to 1. Does that make sense? So each permutation corresponds to a particular perfect matching in the complete graph, right? So these monomials are exactly encoding these perfect matchings. And now here's the thing, right? So the graph G has a perfect matching is equivalent to what? G has a perfect matching if and only if, let's say, well, there is a matching which we can encode by a permutation, right? Like sigma, such that, well, all the variables yi sigma I are in the matrix, correct? But if all these entries yi sigma I, they're in the matrix, right? They're the entries of the matrix, then what happens is that the monomial, right? So let me write it in a different color, right? So this is equivalent to the monomial minus 1 to the sigma with this particular sigma, right? Minus 1 to the sigma times the product of yi sigma I is a non-zero monomial. Of the determinant of x, of xg, right? Like our matrix that we get from xg. But now, if our matrix, like if this monomial is a non-zero determinant monomial of the determinant, notice that there's only this monomial, right? Like with these variables, right? Because each matching corresponds to a different permutation. So in particular, we know that the determinant of this xg that we just constructed, right, has a non-zero monomial. So it cannot be the zero polynomial. Does that make sense? So that's the connection here, right? And this result, again, just a little bit of history, was first proved by Edmonds, okay, who was here in Waterloo back in the day, okay? So this is an in-house solution for all of you, right? So, all right. So now we know that G has a perfect matching if and only if the determinant is a non-zero polynomial. And now, well, testing if G has a perfect matching then becomes a special case of the polynomial identity testing, because now we have this polynomial, which is the determinant, and we want to test if this polynomial is zero or not, right? Because this determinant being zero means that my graph has no perfect matching. Determinant is different from zero. We know that my graph has a perfect matching. Does that make sense? So this equivalence reduces the bipartite matching problem to just testing the polynomial identity testing. So now what do we do? Well, now it's simple, right? So what is the algorithm? Just evaluate determinant of x at a random value for these variables yij. Does that make sense? That's it. Then we're done. Okay, that's the simplest algorithm you'll see, right? For testing a bipartite matching. Okay, and all you needed to know was this polynomial identity testing, right? Okay, and you can say, well, bipartite matching for, like matching for bipartite graphs is easy. We know many algorithms for it. What about the general case? Well, it turns out you can also do the general case. And if you want to see, I made all the lecture notes slides, like you can see it, but due to the sake of time, I won't do it here. I can cover it over office hours, but if you want, you can look at the slides, right? So I'm just going to flash forward. And again, it was also done by Tut, who was also a faculty here in Waterloo. So lots of history and reasons to be proud. Okay, so then we can keep going. And we can discuss this over office hours, right? But then you may ask, okay, sure, we learned this randomized algorithm is one line, but where's my parallel algorithm? You said something about parallel algorithms. Well, so we have seen this randomized algorithm for bipartite matching, right? So why did I say parallel algorithms? Is because of the reason of the following. So the algorithms for matching consisted of doing what, right? I just construct a matrix and a symbolic matrix, and then we need to test if the determinant of that symbolic matrix is 0 or not, right? And we do that by evaluating it at a random point, correct? That's all the algorithm that we came up with, right? That was our algorithm. Now, how do we make this algorithm parallel? Well, it turns out that, well, first of all, the short-zippo lemma that we learned, right, tells us that this algorithm will succeed with high probability, right? So that's correctness is okay. But what about parallel running time? It turns out that we can compute the determinant efficiently in parallel, okay? So, and this, if you want a final project, is a great final project. Great final project. Okay, to compute the determinant efficiently in parallel, which we're not going to see in class, but is a perfectly awesome topic to figure out. Okay, so all right, so now we discussed a little bit the now, sorry, my application closed. Okay, my bad. Okay, let me share again. Don't know what happened. All right, yeah. So now we saw that, well, if you believe me, right, that we can compute the determinant efficiently in parallel, then you get right away a randomized parallel algorithm for computing bipartite and non-bipartite matching, okay, for deciding this problem. Okay, so this is pretty cool, right? Because sometimes we do want parallel algorithms, and all the other algorithms that you learned in class for even for the bipartite matching problem do not run fast in parallel. They're sequential algorithms. Okay, so this is just one cool application to parallel computation. All right, having said that, let's go to the last part of this lecture, which is the isolation lemma.